Okay, we are going to talk about root-locus analysis in this lecture. Root-locus analysis. Yes. In this chapter, we have demonstrated the importance of the poles and zeros of the closed-loop transfer function of a linear control system on the dynamic performance on the system. As we know, all poles and zeros will be affect on the dynamic of the system. The roots of the characteristic equation also determine the absolute and relative stability of linear system, as we know. Root-locus analysis, this is a method, this is a graphical method. It is a graphical analysis and also designing method for control systems. Yes, for a standard system, such as this kind of standard system, we have an input as Rs, the forward path gain is Gs, and the output Ys with the feedback through the Hs. Yes, for this kind of system, closed loop transfer function can be given as Gs over 1 plus Gs Hs. For this system, we know open loop transfer function is Gs times Hs. But this is closed loop transfer function. Okay, for the stability, we have to investigate the characteristic equation, which is given by 1 plus Gs times Hs will be equal to 0 or set to 0. This system, for the characteristic equation, we can give the Gs times Hs as K times Qs over Ps. Here the order of the Q will be assumed at M and the order of Ps assumed as N. So with some assumption, which is K is greater than 0 and equal and greater than M, we can use the root-locus method. How? Now we'll talk about some basics of the root-locus. Let me number some equation here, 1, and this is 2, characteristic equation, and this is 3. Characteristic equation from equation 2 and 3 can be written as 1 plus KQs over Ps will be 0. So we can also write it as Ps times KQs over Ps. This is the characteristic equation. Let me number it as 4. Please note that it's important to say this. The variable parameter k appear as a multiplying factor of Gs Hs for root-locus of a control system. Should always be, okay? So we have to get Gs times Hs as this form always to investigate the root-locus analysis. Let's do an example about it. example, we have s plus 1, s plus 2, plus s square plus 3 plus 2k s plus 5 will be 0. This is the characteristic equation of a system. Let me find the GS, HS from this equation. It means we can say 1 plus HS is written as s plus 1, s plus 1, s plus 2, s square, 3 plus 2ks plus 5 is 0. So we can write the same equation as like that. 1 plus 2ks over by s plus 1, s plus 2 plus s square plus 3s plus 5. We can write it as like that. So now we can say qs over ps, which is given before as this form here, can be written as 2s over s plus 1, s plus 2 plus s square plus 3s plus 5. Okay, this is the qs over ps for this system. Now, as we see in this equation, qs over ps or gs times hs is isolated from k, and so we have a multiplying factor as k. So actually we did it. gs times hs will be written as k g1s h1s. To do some analysis, let me number it as 5 maybe. Yes, 5. Number with 5. So here g1s times h1s does not include the variable parameter k. Okay, by using it with the characteristic equation, we can say g1s times h1s will be equal to minus 1 over k. Let me number it as 6. So we can write some condition now. Condition on magnitude can be written as g1s h1s will be equal to 1 over k. This is given for minus infinity k to infinity. Yes, let's define it as 7. Also, we can write a condition on angles. As g1s h1s will be equal to 2k plus 1 times pi, where k is equal and greater than 0. It means odd multiples of p radians or is 180 degrees, and it is defined as 8. The same condition can be given G1s H1s 2k pi 4k less than 0. Here k is equal to 0 plus and minus 1 plus and minus 2, and it will be continue as like that. So we can understand it is an integer value. So in practice, the condition stated in this equation plays different roles in the construction of root locus. Once the root locus are drawn, the values of k on the root locus are determined by using the conditional magnitude condition. The construction of root locus is basically a graphical problem, although some of the properties are derived analytically. The graphical construction of the RL means root locus, based on the knowledge of the poles and zeros of the function. Which function? Of course, open loop function. It means GS times HS. Open loop transfer function. So, as a general form, GS times HS can be written K G1s H1s s to power of m and blah blah over by s to power of n and blah blah. This is defined as 10. So applying the condition 7, 8 and 9, equation 7, 8 and 9, we can write G1s H1s will be equal to multiplying from I to M S plus ZI over by the multiplying from 1 to N S plus Pj, which is 1 over K. It can be defined as 11. And the angle condition G1s H1s, the angle of it will be equal to sum of from I1 to M S plus ZK, of course the angle, minus the sum of J1 to N, the angle of the S plus Pj. It is defined as 12. So once the root locus, which is called as RL, are constructed, the values OK along the RL can be determined by writing equation 11 as the amplitude of K will be I1 to N S plus Pi over by m j from 1 to m s plus z j. The amplitude of it, of course, it can be defined as 13. So the value of k at any point s1 on the RL is obtained from 13 by substituting the value of s1 into the equation. Okay. To illustrate the use of 12 and 13 for the construction of the Root-Locus, let us consider the function gs hs is k times s plus z1 and s plus p2 s plus p3. Maybe we can show it on the s plane to understand easily. Imaginary axis and real axis. Let us insert all of the poles and zeros at random or arbitrarily to the s-plane. Okay, here and here we have poles minus p2 minus p3. We have 3 poles and a 0. Assume that we have a point at here which is s1. So we want to find it now. Okay, from 0 we have a vector as like that. From p2 we have a vector p3 as like that, and z1 we have here a pole. All of our vectors as like that. So we have some angles with respect to the real axis, always positive real axis. This point theta p1 for the positive real axis, theta p2, theta p3, and theta 0, 1. And the length of the vectors B, A, C, and D. So the angle condition can be written for this graph. Where is the angle condition? Yes, here, from 12. The sum of the zeros minus poles. Theta z1 minus theta p1 minus theta p2 minus theta p3 should be equal to 2k plus 1, 180 degrees. This is 14, so it can be defined as 15. This is the angle condition, which detects that this point is on Root-Locus or not. Okay? To specify this, we will use angle condition. And the magnitude, if we have a point on the Root-Locus as S1, what is the gain? What is k value for this point? To find it, we will use magnitude condition. Magnitude condition, which is given as before. K will be equal to vector length of the poles over by the product of vector length of zeros. So it will be on this graph, as you see, the poles has B, C, and D. So we should write it B times C times D over by, what about the 0? As you see here, A we have only, so over by A. it gives the k value for this point. To test all points on the root locus is on or not, and to find the all k values regarding the points is not an easy task manually, so we can use computers to do this, but of course we have to know how can we do it manually. Okay, first of all we have to know some properties of the root locus. Now we'll continue from properties of the root locus. We have to know k can be 0 and k can be plus and minus infinity. How? At the poles, all poles value, we get k as 0 for all poles. And we have to know for all zeros, we have k value as minus and plus infinity. Okay, let's do an example. We have a characteristic equation as s plus s times s plus 2 s plus 3 plus k times s plus 1 will be equal to 0. For this system, which characteristic equation given as like that, we can find gs times hss k s plus 1 over s plus 2 s plus 3. Okay, we can insert these points on the s plane. Imaginary axis and real axis. We have a pole at 0, 1, 2, and 3. We have a 0, maybe we use different color. We have a 0 at minus 1, a pole minus 2, a pole minus 3. Okay, minus 1, minus 2, and minus 3. So with this information, we know at this point k will be equal to 0. For the 0 point, k will be plus and minus infinity. That's all. We have to know this information also. What about the number of branches on the root locus? Number of branches on the root locus. The number of the branches is equal to the order of the polynomial. What does it mean? The order of the denominator, of course, of the open transfer function. For a root locus, we know k value is investigated from 0 to infinity. So root locus branch will start from the poles to the 0. Okay, zeros. Let's do an example. If we have s plus 2, s plus 3, and k times s plus 1 will be equal to 0. For this characteristic equation, what we have as a number of branches, for example. For this characteristic equation, we can write G as HS as K times S plus 1 over by S, S plus 2, S plus 3. What is the order of this equation? 3. So we will have 3 branches. Another important property is symmetry of the RL. It is important to pay attention to the symmetry of the root locus. Let's do another example here. S, S plus 1, S plus 2 plus K will be 0. So GSHS can be given as K over S, S plus 1, S plus 2. How many number of branches? 3, because the order of the polynomial is 3. How many zeros for this function? Maybe we should talk about it also. Let's turn back to this example. We have 3 poles. What about the zeros? Again, we have 3 zeros, where minus 1, infinity and infinity. Okay, we should always have the equal number of zeros and poles. How is this possible? If you get a limit for this function, maybe we should do it. Limit s approaches to infinity. Let we get s parenthesis sk 1 plus 1 over s over by get the s to power of 3 parentheses. We have, okay, here we have 1 plus 2 to power of 2 over by s, 1 plus 3 over s. Okay, so here we can write it as limit s approaches to infinity k 1 plus 1 over s over by s square 1 plus 2 to the power of s, 2 over by s, 1 plus 3 over by s. So here, as you see, we have 2 zeros for this function at infinity. Okay. Let's remove this part now. Okay, for this function, for the new example, we have third order system. So we should have 3 branches. Okay, and we have 3 zeros at infinity, infinity, and infinity. Let's draw it now. Yes, j omega and sigma. We have a pole at 0, a pole at -1, a pole at -2. 0, -1, and -2. We know Root-Locus start from poles to the zeros. So it means all locus diagram will start from 0 poles, and it will be end at the infinity. Okay, how it is possible? You will see later more detail. If you draw this Root-Locus diagram, it will be as like that, and in this part it will be goes to the infinity, k goes to the infinity, k goes to the infinity, and k goes to the infinity. Okay, at the pole point k is 0. This is the symmetry property of the RL, because as you see, a branch will goes as like that, and the symmetry with respect to the real axis will also the same as like that. Okay, it says symmetry of these branches. Okay, another property is angles of asymptotes. What does mean? Behavior of the RL where at s is equal to infinity. Okay, asymptotes mean behavior of the RL at s is equal to infinity. We can find the angles of the asymptotes with this formula. Theta I will be equal to 2k plus 1 over by n minus m. And as you know, the denominator of the open loop transfer function order and the order of nominator of the open loop transfer function is m times with 180 degrees. Okay, with this formula, of course, n is not equal to m. This formula is defined as 16.